So application-wise, we do catalysis in our labs, and of course, we try to do green catalytic processes. So we try solvent-free catalysis or water as a solvent. We obviously try to make our catalyst recyclable because that's the point of having a good catalyst. So we use magnetic separation and biphasic processes, and we also do hydrogen evolution reaction and CO2 conversion. So electrochemistry in collaboration with Northwest University in South Africa. Yeah, I'm just showing you an example of one of our beautiful bimetallic nanoparticles. This is actually magnetite with the outer shell being copper nanomaterials. And we're using this as one of our catalysts because it will be very easy to recover, from your products. And then we also do water treatment. I'll be talking a little bit about this today, the extraction of PGMs from acid mine wastewater. We also look at treatment of dyes in textile wastewater. And most recently, we tried to make antimicrobial nanomaterials for harvested rainwater treatment so that perhaps in our poorer communities, we can add something to the water, the rainwater, which can make it potable. And then this is just one of our nanomaterials we've made. This is actually silica, the lighter ones, with discrete gold nanoparticles tethered to the silica nanoparticle. And these were used in one of our dye degradation studies. This has also been published by Springer Nature Applied Sciences. And then finally, I collaborate with physiology and health sciences at our university because we send our nanomaterials for treatment of coagulated blood clotting, for cancer treatment, and also for TB treatment. So the whole purpose of my research, I would say, is, as I said, we study the nanomaterial and we think, what do we want to use it for? We design it, and then we do the application. That's just an example of course, one of the biomedical applications, not mine, literature example. But so that brings us to our topic of today. So usually we try to do nanomaterials or nanoparticles, which is less than 100 nanometer. We actually make nanomaterials, which is about between 1 to 10 nanometers, up to 20 and maybe 30 nanometers, depending on what we use it for. So iron oxide nanoparticles have superparamagnetic properties because once it's magnetized, these particles will behave like small permanent magnets. And once you remove the magnetic field, they don't retain any residual magnetism. And this is just an example of that. This is, for instance, magnetite in water. It's a suspension. When you add the magnet, you can clearly see it's attracted to the nanomaterials. The nanomaterials are attracted to the magnet. And when you remove the magnet, you will see it will disperse again. And because of this, obviously, these magnetic nanomaterials have been applied in several applications that we show here, amongst others, electronics, environmental, cosmetics, and transportation. So talking about platinum group metals, PGMs, we usually talk about these 6 metals when we talk about platinum group metals, but some people also add silver and gold in their studies because that's also precious metals. And South Africa actually is the largest exporter of or producer of platinum group metals because of our mining industry, of course. And there are 2 ways that they can do this extraction of our metals. The first is pyrometallurgy, and this involves smelting, roasting, and then calcination. And then the second method would be hydrometallurgy, and this involves leaching, solution concentration, and then metal recovery. And within this, there's several ways of doing it, which is chemical precipitation, solvent extraction, ion exchange processes, and of course, magnetic solid phase extraction, which is what we'll talk about. So I've mentioned Professor Klaus Koch, lovely man, and it's the PGM extraction is his area of expertise, and we collaborated with the idea that we want to make these magnetic nanoparticles at the time. This was 8 years ago when we proposed this PhD project, because we wanted to see, would these unmodified ions or magnetic nanoparticles be able to actually extract metals from acid mine wastewater, and then obviously we will remove it with a magnet and try to desorb it so that we can recover our metals and then reuse our magnetite nanomaterials. So that was the plan. And at the bottom, you can see here, it's a little dark, but there's the nanomaterials, there's the magnet, and you can see how it's attracted to the magnet. And it's so strong, this is a very heavy magnet, that it can even hold, the nanomaterials can hold the magnet to the beaker. So this was our plan. And so making magnetite is very easy. It's a literature method. You basically need an iron 2 and an iron 3 source, and you reduce it with ammonium hydroxide. Over time, you will see this black precipitate forming, and then you have your ions. It's really simple to make. The problem is you can get different types of iron oxides. You can get hematite, megamite, goethite, and you just want magnetite because that's the most magnetic nanomaterials. So my student did different experiments with temperature and the variation of the ion concentration. And we actually found that at a temperature of 60 degrees Celsius, with all three concentrations, we form the most pure magnetite without any other impurities. And this was confirmed with IR and PXRD. So this is how we continued making these nanomaterials. We also analyzed it via HRTEM and PXRD, and the nanomaterials that we formed were quite monodispersed. They were between 10 to 12 nanometers in size, which is quite excellent and beautiful. So I've mentioned this is adsorbent 1 because I want to tell the story of how we got to modify these magnetic nanomaterials. So once we did the application, which is basically simulating acid mine wastewater, adding our materials, and then removing it, we did ICP on the remaining solution. And the results that we got was that with even 10 milligrams of adsorbent, you removed about 100% of gold in 80 minutes, which is excellent. And of course, if you increased your amount of adsorbent, so for 30 milligrams of gold, 100% extraction within 3 minutes. And that's kind of pretty excellent results. When we tried this with the palladium, we saw that using these low amounts of adsorbent gave very low extraction rates. So for the 30 milligrams, where we got 100% for the gold, we got about 30% for the palladium. So we increased it a bit to 60 and 90, and still the most we could extract was 60% of the palladium. And this is single batch studies still. So then when we did platinum, we found that increasing from 30 to 60 to 90 didn't actually make much of a difference because you extract between 70 and 85% of your platinum as well. So when we looked at the effect of the metal species, it could be clearly seen that the more metal concentration you have, the lower your extraction rate would be. And of course, that makes a lot of sense. And then when we varied the pH, now our acid mine effluent, I'm checking my time, there's still a lot of time. The acid mine effluent is usually at a pH of 1. So we checked pH 1, 3, and 5. And what we found was at pH 5 and 3, we increase our gold concentration, of course. You still get very good extraction after about 40 minutes, 100%. But at pH 1, look what happens. You get very little gold extraction compared to the other pHs. So when we looked a bit closer, we realized we monitored the iron in our solutions, and we realized over time that so much iron is leached from our nanomaterials at a pH of 1. Of course, this means our adsorbent, our magnetic nanoparticle, which is such an excellent extractor for gold, is not stable at a pH of 1. We also did some characterization of our materials after it's been adsorbed. And we saw, obviously this is magnetite, and this is at a pH of 1, which we didn't extract much gold. But for the pH 3 and pH 5, we saw these peaks, which is for metallic gold. So it seems like there's a layer of metallic gold on our nanomaterials after extraction. We couldn't see the same for the palladium and platinum, or even though we know it extracts. But remember, we used 3 times more adsorbent for the palladium and the platinum, and they extracted also very little of the metals. So we weren't able to see this with the palladium and the platinum. So because of our research history, if I can call it like that, we now had to decide to modify these ions to try and make it stable, and it must still be a good extractant. So we know that dendrimers, we've seen it with our other nanomaterials, can stabilize a nanomaterial on the outside. So we thought if we had our ion and we have our dendrimer stabilizing it on the outside, the dendrimer itself should also be able to actually coordinate to metals, because it's a well-known fact that metals coordinate to the interior of dendrimers, because this is how dendrimer encapsulated nanoparticles are actually made. So this is how we came to this idea of immobilizing dendrimers on the surface of our ions, and to see, will it protect and stabilize our ion or our ion, or will it not work at all? So we took commercially available G3 DAB PPI dendrimer. We modified, this is water soluble. So we modified it with alkyl chains of different lengths, C5, C10, C15. We found the C15 one to be the most stable, and we call this a dendrimer micelle because the exterior is hydrophobic and the interior is hydrophilic. Also, this is soluble in organic solvents, so it makes things much easier to work with. So then looking at how we wanted to stabilize our ions, if this is our unmodified ions, we decided, let's first just take our dendrimer micelle and just mix these two together. So the naked spines and the dendrimer micelle was mixed together for a few days, and then we removed it with a magnet. And this would obviously be a nanocomposite, and there's no sort of uniformity or anything. So we thought, how else can we put this dendrimer on the ion? And from the literature, we could see you could use these aliphatic chains also and bind it directly to the surface of the naked nanoparticle. So this was done by first reacting iron 2 and iron 3, then adding your aliphatic chains, then reducing it. And this is how we get these alkyl chains on the surface of the dendrimer. And one could see this would stabilize actually a dendrimer nanoparticle very well. That's what I would think. And then for our fourth adsorbent, we actually saw that people use these types of nanomaterials with dendrimers because this alkyl chain over there and this alkyl chain over here will intercalate, and it will have very strong intermolecular forces. So we reacted these two together to form adsorbent 4, and also this should protect our nanomaterial as well as be able to extract metals from our solution. So this is how we got to our 4 adsorbents. So looking at the HRTEM of it, it makes quite a lot of sense. This is the naked or unmodified nanoparticles. This is adsorbent 2, which I expect to look a little messy because it's literally the dendrimer micelle and the naked nanoparticles. Adsorbent 3 looks a bit better than adsorbent 1, and this of course is because it has these alkyl chains stabilizing it on the surface. And then adsorbent 4, as you can see, it looks like a big mess as expected because it's your adsorbent 3 plus your micelle. But still we wanted to see, you know, what will we get. So basically for adsorbent 3, we got nanometer diameters of 13 and 0.2, 13.5 for adsorbent 3, and adsorbent 4 quite stable at 10.3. So obviously we first did the stability study because we wanted to see, will this now work or not. For adsorbent 1, we can see a lot of our iron leached out at pH of 1. Adsorbent 2, less iron leached, but still it was not very stable at a pH of 1. For adsorbent 3, surprisingly, I thought this would be very stable, but although it's less than the other two, it still leached some iron. But for adsorbent 4, and everything is done in triplicate, we saw no leaching of iron at a pH of 1. So we have an adsorbent, which seems to be stable at pH of 1. And the question was now just, will it also extract nanomaterials? The metals. So we did competitive adsorption after this. So we did a mixture of our gold, palladium, and our platinum species because we wanted to see, well, what will it extract first? And if we compare the naked Mayans with the second adsorbent first, you can see the naked Mayans, as we said at pH 1, extracted 100% of the gold selectively, but unfortunately it's not stable at pH 1, so you can't reuse it. So this is what the problem was. And as you increase the pH, it still extracts gold first, and then platinum, and then palladium. Yet at pH 5 and 6, where it seems like the palladium extracted a lot, this is actually because the palladium precipitates out of solution at high pHs, so this can't be attributed to adsorption on the surface of the naked Mayan. If we compare it to adsorbent 2, which is our nanocomposite, very beautiful. We can see, yes, it absorbs gold, but it also absorbs quite a lot of palladium and platinum. And of course, this is because probably this coordinates to the interior of the dendrimer micelles itself. And we can see at all the pHs, you actually extract quite a bit of all the metals. Again, at pH 5 and 6, we don't know if this is due to the precipitation or because of the coordination to the dendrimer micelle, or the dendrimer rather coordinating, the internal amines of the dendrimer coordinating to the metal. So looking at the Mayans versus adsorbent 3, not surprisingly, this was not a good extractant. I think at pH 1, it shows it extracted a lot of gold. But at pH 1, remember, this still decomposes. So probably the surface that's open now extracted the gold. But as you increase the pH, and this is more stable, you can see a very clear decrease in adsorption. And again, the palladium, this now we can clearly say is due to precipitation. So this was not a good extractant at all. But of course, for adsorbent 4, as we can see, it definitely extracted gold first, and it also extracted a little bit of platinum and palladium, especially as you increase your pH. So it's a good stabilizer, stable at pH 1, and it extracts actually our metals. And we can even say it's more selective towards gold because it extracts more gold than the naked mines at these pHs. And again, this and that, the palladium, could be due to the precipitation. So we looked at desorption studies and we used stripping agents, nitric acid, thiourea, and then a mixture of the stripping agents. And we saw that actually for the naked mines, this was easily desorbed. For adsorbent 2, in all cases, we can say the mixture of the nitric acid and the thiourea gave the best desorption from the adsorbents. For the third adsorbent, this would be because there was not much to adsorb in the first place, so therefore it only desorbed gold. And then surprisingly, or not surprisingly, for adsorbent 4, we desorbed very little metal, and even the mixture desorbed little of the metal, even though it extracted so much. So this could obviously mean that the metals are coordinated quite strongly to the interior of the dendrimer. So we have to look at different stripping agents for that, or we could perhaps try to reduce it and form nanoparticles and extract it from there. Or we could use this in an application for something else as well. So in conclusion, we actually tested unmodified spirins, and they were good adsorbents, but they dissolved at low pH. And therefore, we modified our spirins with carboxylic acids and dendrimer micelles. We found that both the unmodified and the dendrimer modified spirins actually proved to be efficient absorbents for the competitive adsorption of our metal species. And the dendrimer modified spines remain stable at very low pH and still show good extraction. So our adsorbent 4 is quite beautiful and excellent. And depending on the adsorbent that you use and the stripping solution that you use, you can desorb the metals from the adsorbent and reuse the adsorbent. We did preliminary recycling of the adsorbent. And then finally, we collaborated, let me show rather the next slide, which Nasran already showed, but we collaborated with one of our mining companies in South Africa to actually, because this was lab study, so we want to see what happens with the real acid mine containing PGM, acid mine water containing PGMs. This is an actual picture of it. So we have our naked adsorbents. We want to see what happens if we add it to that. How will it extract? And of course, we can desorb it and reuse it again. So I just want to acknowledge the student who did all this work. This is Sipiso Kutlani. This was a PhD study, and she completed a PhD, and she's currently actually looking for a postdoctoral fellowship right now, if anyone is interested. And Jez, Joshua, and Gerbrand contributed to some of the other studies, like the binding studies and the bimetallic nanomaterials. I'd like to thank Tutuka NRF and Stellenbosch University for research funding. And also I would like to thank Springer Nature Applied Sciences and Nasran for giving me this lovely opportunity. It was very nerve-wracking, but thank you so much.
Thank you. Thanks a lot for your great presentation and sticking to the time. So we have now definitely time for some questions. If, as I said, just I can read the questions if there is anything in the chat box. And I just to start, you mentioned that in South Africa you have now a collaboration with industry, and basically you are really using these methods and trying that. So do you think that in an international scale, there is also interest, and like which countries can have the same problem, and do you have like kind of international collaborations?
I would love to find international collaborations. We haven't done so yet because these materials have so much potential, because if you just change the dendrimer itself and the dendrimer generation, you could probably make the adsorbent selective for a specific type of metal. So maybe the different dendrimers will select different metals. So, and sometimes even after all their processes, there's still small bits of metals. Apparently, I don't know much about the mining industry, but left in the effluents. And this is where these types of materials could come in. But I would, of course, be also very interested in international collaboration if I get some interest in it.
Okay, perfect. So any questions just for Rehana? I am checking the box.
Here it is my question.
Yes, you can also ask your question. That's absolutely fine.
Okay, first of all, I would like to say thank you for your nice presentation, which is somehow related with my previous publication papers. Fortunately, my paper is also published on your journal, this SN Applied Science.
Okay.
That is synthesis and characterizations of hematite and magnetite nanoparticles, which is extracted from the iron-based industrial wastewater sludges. That is electrocoagulated sludge. That is what I am hearing with your presentation, with exciting knowledge and experimental investigation, what I have seen it. So my question is, you may see my papers, 2 or 3 papers previously published on, one of the paper is from your journal and the other is from other journals, you can search it. But I generally used for the iron-based oxides recovery and used for wastewater treatment, especially in organic and organic contaminant removals used as an adsorbent.
Yes.
The first paper is used for dye-contaminant removal. The nanoparticles that I have extracted or recovered is hematite and magnetite from electrocoagulated sludge from textile wastewater treatment plants. And also I have gone through in detail what has been the characteristics of that adsorbent is that the paper is now published in your journal is the detailed morphological, crystallinity, and the other nanoparticle properties have been characterized and published in this SCN Applied Science. And the third paper that has will come soon is specifically used for inorganic contaminants, that is fluoride, which is ion exchange type of an adsorption is process will carried out or going on. But
sounds good.
The method that I have used is only the calcination and beneficiation process. You see that how much the purity is not yet investigated.
Yes.
But the XRD crystallinity tells us something which is the pure crystalline that mostly contained in hematite. Yeah, magnetite.
Magnetite.
Basically, the hematite and the magnetite types of iron oxides.
Yes, so that is why we optimized our experimental procedure, because we just wanted only magnetite. So all the experimental details are actually in the paper, so you can download it and you can see how we managed to make very pure magnetite.
Yeah, that the XRD crystallinity tells us that this purely magnetite is produced. But we have not yet seen that the exact purity of this, the magnetite only, or the other contaminant will be appear, because the waste is containing a number of matrix wastes, some of the other heavy metals or other organic compounds. Actually, the organic compound or the organic contaminant will remove with calcination. I have used only the calcination type of treatment. But I doubt that some of the heavy metals may be exist in the adsorbent that has been synthesized. So how could I assure that whether this heavy metal will be appear or not together with this magnetite nanoparticles that have been synthesized and produced?
You mean after you've extracted it?
Yeah, first of all, I have used the wet treatment process, that's beneficiation, with a simple deionized water, and then I have used the decalcination up to 500 temperature, degree centigrade temperature.
So
This is
you're trying to make magnetite with a metal on the surface?
yeah.
Oh, okay. Yes, you must read all my other papers. But you could email me, Tadile, set your name, Tadile.
Yeah.
You can really email me and then I will be able to give you some advice on how to do this, because there's several different ways to actually immobilize metals on magnetic surfaces. And we've done it by reduction, we've done it by using tethers on the nanomaterials. So I think if you email me, we can have a discussion and I can give you some advice.
Okay, thank you very much. And in addition, with this regard, yeah, I have seen your paper is very interesting and it needs a lot of collaboration in the globe. So your research
Open
work
to
is
it.
on acid mining waste. It is a liquid waste, but my work is on the electrocoagulated sludge. Somehow 90% is similar with you.
Yes.
So we can collaborate and do a lot of researches with regard to this waste to valuable products. So we can
Okay,
change the waste
yes.
into the valuable products.
The acid mine is just one aspect. As I said, I also work on wastewater treatment, like you said, the treatment of dyes in textile wastewater, and also trying to make rainwater more potable. So all types of water treatment, because nano is the future.
Yeah.
For you, you're in nanotechnology.
Thank you very much.
Thank you. Yeah, so that was the collaboration. That's a good achievement from the webinar. We hope for that. So thank you, Rehana, again, and thanks all the participants. And hopefully, yeah, you will go on, or probably already know Rehana and her work. And please, if you have any questions about her research, you can contact her. And if you had any question about our journal, you have my email address. So don't hesitate to contact and ask your questions. So if there is no question, no, I can see something. Okay, so just give me time. Now there are some questions. Okay, the first question from Tobias Depri. Sorry if I pronounce the names not correctly. So he has two questions. The first question is about the application of nanoparticles on the wastewater. Is it possible to use a flow through reactor, maybe nanoparticles immobilized on a surface, or it can be considered more as a discontinuous process?
Tobias is an engineer. Tobias, so what I want to do when I treat wastewater, especially wastewater which we want people to be able to drink, because obviously it's a problem in our country that not everyone has, good quality drinking water, is not wanting to use a reactor. I would think I want to make my nanomaterials. I want to be able to add it to the water, remove it with a magnet. So everything has to be safe. We should know that. And then perhaps have the water be obviously purified and good enough to drink after that. Because even though you can add your things to harvested rainwater, I've heard bacteria keeps growing there over time. And so it might be safe today, but tomorrow it's not safe anymore. Another technology would be to make membranes, nanomembranes, which you can put, one of our colleagues actually did that, put in a water bottle, basically as a filter. So if you get to river water, you scoop up, you fill up your bottle, you put on your cap, which contains the filter, and you should be able to drink the river water because it just keeps out all the nasty stuff. So we're looking at solutions like that, real life applications that we can help people with. Well,
Okay. Perfect. And I have the second question. So regarding the application of nanoparticles in CO2 capturing, which methods do you consider for such an application? I don't know if you can comment.
In what capturing?
CO2.
Oh,
Carbon monoxide.
I don't want to reveal my secrets, but,
Okay.
but I'm looking at metal. And we've made actually an amazing nanomaterial, which we will, it's not published yet, so I can't say much about it. But the idea is to not only capture CO2, but then convert it as well in one go. That's the idea. To something like fuels, etc., etc. But yeah, I can't say too much about that right now.
Okay, but that's good to know that two people are working on that.
Yes.
Okay.
I should ask Elon Musk some money. Oh my God, yeah. He was giving 100 million.
Okay. So, yeah, in the chat box, there are some emails that probably, Rehana, you can just also share
I
your
can't see
email.
the chat right now. I'll only be able to
Okay.
once I stop sharing.
Yeah,
I think.
probably.
Mhm.
So, but I'm happy that we could just connect the scientists through this webinar together. Yes, and as I said, don't hesitate to contact Rehana for more collaborations. And I just once more, I want to thank you for participating, and hopefully you will join our next webinars, because I'm sure we would have a lot of webinars on similar topics, as we have many articles on these topics. Okay, thank you.
Thank you so much.
Thanks.
Thank you for the
So
opportunity.
have a nice day and see you next time.